Okay, there will be 15 questions, 15 to 20 questions, and we'll give you 20-25 minutes to solve it. Okay, multi-choice questions. The first quiz will happen next week. Is that okay?
Is it possible, sir, if you can share some sample questions?
Well, it's simply can, but it's when they are factual questions on things that has been covered so far in the class. So if you brush up whatever has been covered in the class, that should be enough. Okay, let us start now today's class.
Sorry for
So
interrupting. Just one question. So you said next Sunday. Is it next Sunday or Saturday?
I mean, yeah,
Okay.
my bad. Yeah, next Saturday, yeah, next week.
Sir, one more question I had. Whatever we cover in today's class is also going to be included?
Of course.
Okay. And sir, I remember we have already discussed this in length, but on the first class, there was a lot of back and forth between what was our final decided grading policy. If you can just summarize it quickly once again for the sake of clarity,
Yeah,
it
we
will be
have
really.
done that. Please, no, please don't do this. We have done this. No, it is documented. It is written down. You look at this. See
Okay,
my
this is the
screen?
final one, right? Yeah.
Of course,
Yeah.
right? I wrote it and said that this is final. We are not going to discuss this anymore. Please don't do
Sure.
this. Okay.
Thank you, sir.
Okay. So it is there. It is written. Just have a look at it. I see one other hand raised. Nirmit, just go on.
Yeah, so sir, for the quiz, will there be like we have studied sigma algebra, Borel, sigma. So will there be calculation for this or only, as you said, factual? Am I audible?
Brush up whatever.
Sir, your audio is not very clear.
Yes, sir. We are. You are breaking.
Hello. Is it okay? There should be some problem with my internet today. Just a minute. Give me a minute. Hello. Am I audible?
Yes, sir. Now you are audible.
Okay. In my internet slows. Yeah, I said it is just your. It is about testing what you have understood from whatever has been taught. Okay, it will mostly be factual with 3-4 options for each question, and there will be 15 questions and 20 minutes. Okay, that is
Okay.
what's going to be.
Yeah.
Okay, let us start then. Hope that you see my screen. And last class, just a quick recap. Yeah, in last class, we defined what generative modeling is. That we are given data from an unknown distribution. Okay, what we wanted to do is to estimate the unknown distribution and also sample from it. Okay, that was the problem that we wanted to solve. Okay, so we wanted to do it from the perspective or angle of what I called as divergence minimization, where the idea was to assume a parametric form for the density function to be estimated, denoted by p theta, right? Where theta are the set of parameters that are representing the underlying distribution. Okay, so we have p theta that represents the distribution that we are modeling, and we call this the model distribution. And it can be any parametric distribution, such as a Gaussian distribution or even a neural network. Okay, that would take some random variable as input, and the output of that neural network is the distribution of the output of the neural network is taken to be p theta. Then we said, okay, once you have this parametric model, you define, okay, I think there's a typo here. Hmm. Hmm. Why is this not? Somebody tell me what's wrong. I'm not seeing any of these options.
Are you not able to scroll?
I'm able to scroll. Yeah, I'm actually not able to scroll also now. Yeah, now I can scroll. Yeah, okay. There was a typo here. Define and compute. Define and compute a distance or divergence metric between the true distribution and the assumed parametric density function. True density function and parametric density function. Okay, that will tell you how close or far px and p theta are, where px is the true distribution and p theta is the distribution of interest. Okay, and then you adjust or compute the parameters of p theta such that this divergence metric is minimized. Okay, this computing the parameters of p theta such that this is minimized is what is called as training or learning of the model. Okay, mathematically it is solving an optimization problem over the space of the parameters of the density that we have assumed. Okay, yeah, so the final estimate of px is p theta star, where theta star is the set of parameters that we have obtained by solving the above optimization problem. Okay, that is what we saw. And also we quickly saw one definition, one of the possible definition for the divergence metric, which we call the Kullback-Leibler divergence or KL divergence. Okay, okay, so I want you to, I'll stop here for a minute, and I want you to let me know if you have any questions on this general philosophy of divergence minimization, because that will be the central theme of most of the models that we'll be seeing in this course, right? We start with a parametric form for the density, okay, that we want to estimate, and we define a divergence metric. Now that divergence metric becomes a function of the parameters of the underlying density. Then we compute the, or rather we get the parameters or of the density by minimizing the divergence metric between the true density and the parametric density. So that is the idea. Any questions on this before we move on? Am I audible? Hello?
Yes, sir.
Okay. No questions? Okay, great. Let us move on then. Okay. Now we will look at the first class of family of generative models that we will see. We are called adversarial generative models, are also called as generative adversarial networks or GANs. Okay. So what is the idea there? So same thing, right? So what we will do is we will given data. Okay. So what is data? Data are some samples drawn from an unknown distribution. What can these be? These are like examples are images of digits or This is what is there in MNES dataset. It can be some features of text and so on. It can be anything. They are given n data points of n data points drawn from an unknown distribution. Okay, goal is to estimate px, and remember we are solving generative modeling here and sample from px. Okay, now what do you mean by sampling from px is that generate more samples from px. Okay, that are not in D. You're given data set, but you want to generate more samples from the data set, okay, that are not a part of the data set. Okay, that is what we want by, that is what we need call by sampling. Okay. Okay. Now, what is the idea? So the first step to do this is that assume a parametric form on Px, call it P theta. Okay, this is what we start from. Now, in the class of generative models known as adversarial network, how do we get P theta? So, in okay, P theta is represented by a neural network. A deep neural network. Okay, it means that there is a neural network. See, whenever I write neural networks, right, in this course from now on, I would be assuming I'll be following this convention that I will write these kinds of quadrilaterals, right, trapeziums, and the shape will be proportional to the dimensionality of the data. Why can't I write a straight line? Better. Okay. Now, what is happening here is that, okay, so before I move on, I am assuming that all of you know how the error backpropagation algorithm works, right? How to train neural networks. Is there anybody who does not know how to perform gradient descents on neural networks? Rather, I will just make it a. Do we need? Yeah, Nirmit, you raised your hand.
I mean, I don't know, but if we can have tutorial on that, that would be good.
Yeah, I can, but that's why I'm asking, right? Do we need a tutorial on backpropagation algorithms?
Yes. I mean, yeah.
Okay, Karthik.
Yes, sir.
Make it a.
Same. Yeah, I was just.
So you haven't trained neural networks before, is it?
Yeah.
No.
Sir, we're broadly aware of how it, like what it's supposed to do, but not with the same level of mathematical rigor that this course is going on with.
Okay, so let us make that an item of tutorial then. We'll teach backpropagation algorithm. Okay, so yeah, it is mostly repeated application of chain rule. Okay, that is what it is. Okay, but yeah, I will ask Chandran to have a tutorial on backprop. Okay, that apart, so I said now P theta will be represented using neural networks. Okay, so now let us call this as some G theta of Z. Okay, now let's say that you have Z, which is a random variable that has a Gaussian distribution associated with it. Okay, now typically, okay, I'll come to that in a while. Now we have this proposition that suppose G is a random variable with some distribution, and G theta of Z be a function, that would map Z, okay, to some other space X cap. Okay, now this result says that Z cap is another random variable with a distribution governed by the function G theta. Does it make sense? Do you understand what I'm saying? Suppose this is a standard result which you will be studying or have studied in random process, that if you have a random variable, okay, and if you have a function that acts on a random variable, then the distribution of the output of that function, okay, first of all, the output of that function is another random variable, and the distribution of that particular output or function depends upon the functional form of Z. So what do I mean by that? Examples. If Z is, let's say, a uniform random variable between 0 and 1, okay, and some G theta of X is equal to, let's say, Z squared, okay, then Z squared can you see my screen?
Yes, sir.
Sir, if you're writing something, then I don't think we are able to see.
Oh, is it? I think it is stuck. Okay, let me just see. Okay, I think, yeah. Z squared will not be uniform. Do you see my writing now?
Yes,
Yes, sir.
Yes.
Okay, great. Yeah, this is what it is, right? I mean, if you have, let's say, uniform random variable and you take the square root of it, it will not be uniform. It will have some other distribution than uniform distribution. Do you all get this idea? So basically, what I'm saying is that you take a random variable that has a particular distribution, okay, and then if you pass that through a deterministic function, the output random variable will have a different distribution compared to the input random variable. Is this idea clear? And the distribution of the output random variable depends on what sort of function you are passing the input random variable through. Is this clear? Okay. Now, why is this important? Let us look at this. The way we are modeling v theta is via this function v theta of z. Okay. Now, this g theta of z. Okay. Let me write that again. G theta of z in our case, g theta of z is a neural network. Okay, just for the sake of completeness, I will define what a neural network is. Now, let's say that Z is in some Rk dimensional space, and we are talking of vector valued random variables here. Okay, so what happens is that in this case, right? I mean, Z is a vector valued random variable with Gaussian distribution. If Z is in Rk, then g theta of z is defined like this. So what you first do is that you take some weight vector w1, okay, and multiply that with z. So what will you get? I will write the dimensions also. Okay, let's say that w1 is a matrix which is in, so z is in Rk, right? So this is L1 cross K. So you have a matrix of L1 cross K. So now when you multiply uh, W1 with Z, what will you get? You will get a R L1 dimensional vector. Can all of you see that? Because Z is actually in K cross 1, right? It's a column vector of K dimensions, which means that you have 1 to K rows and 1 column, and W1 has L1 rows and K columns. When you multiply that, you will get a L1 cross 1 dimensional vector. Can all of you see this? Is it okay? Okay. So then what you do is, this is a linear transformation. Then you do an element-wise non-linearity, where what happens is that when you do this W1 transpose Z, so what is happening is every element of this W1 transpose Z, so this of a vector Z is simply, you take the elements of Z. So Z is actually 1 by 1 plus e power, let me make it a scalar. So this is the definition of the sigmoid. Okay, so now what you do is that when you write sigma of W1Z, W1Z is a L1 dimensional vector. You take every element of it and do this operation 1 by 1 plus e power minus z. Then you still get an L1 dimensional vector. That is what I call by sigma W1Z. Is that okay? Okay. So then what happens is that you take another set of parameters, call them W2, and multiply sigma W1Z with that W2. Now this W2 is of dimensions L2 cross L1, okay, which implies that W2 times sigma of W1Z, okay, will lie in R L2 cross 1 dimensions. Is that okay? Okay, so then what you do is a little further, okay, then you have another nonlinearity here. Okay, then you take another W3 here, and now W3 is, this is L3 cross L1, and you can have another nonlinearity. You'll have W4 and so on. So what is this? This function is actually a 4-layer neural network. Is this okay? So this is what a deep neural network is. I have just written that in a vectorized form, that there are functions, right? I mean, there are linear transformations which are of type W1Z, okay? And then there is a nonlinearity given by a sigma. So there is a linear transformation followed by a nonlinearity. That is what a deep neural network is. I hope this is clear to all of you. Okay, I see some questions here. Yeah, Raghavendra.
Yes, sir. I mean, you have just mentioned W4, so there is no sigma applied to W4, or?
You can. I mean, that depends. No, I mean, if final layer is linear in the case in the network that I have written, you can put a sigma here.
Okay, thanks.
Yeah, I mean that depends. That's a design choice. Now, if this is g theta, what is theta? Theta is all these set of parameters. You know, W1, W2, W3, and W4. This is what I am calling by g theta. Is that all right? Okay, so I'll not write this again. So now training a neural network will be finding out these W1, W2, W3, W4 through solving an optimization problem. And what problem do we solve in the case of generative models is something that we will see now. And how do we solve it is through error backpropagation. Okay, maybe I'll just mention it quickly when we formulate the optimization problem. But anyway, so now do you understand this? So now when I write this diagram, that there is a neural network that takes Z, which has a Gaussian distribution, okay, and there is this function g theta of Z, and you are getting an X cap, okay. Typically, Z is in some RK dimensional space, and X cap is in R D dimensional space, which is same as the dimensionality of your X, because we are trying to model distribution of Px here. Typically what happens is the dimensionality D will be much higher than that of K, which means that you will have to adjust this L1, L2, L3, L4, okay, such that the final output layer will have dimensionality that is much higher than the input dimensionality. And note that it need not be a 4-layer neural network. For instance, right, if you take ResNet 50, there will be these 50 Ws, okay, 50 layers. It's a deep neural network. I've just given you an example of a 4-layer neural network. It can be any layer. And these nonlinearities need not be of this form. It can be of this form also, right? I mean, which is 1 if Z is greater than 0 or 0 otherwise. This is called the ReLU activation. And this is called the sigmoid and so on, right? Doesn't matter, but in general, it is a deep neural network. I mean, as far as our course is concerned, we don't care what the form of these things are. They are hyperparameters and design choices. Okay. So now what we are interested in is that you start with a random variable which has a Gaussian distribution in k dimensions. There is a deterministic function g theta, which is a neural network that would transform it to another dimensional space called that x theta, x cap, and this has the distribution v theta. This is our setting. Okay, we'll take questions here. Aviroop?
Yeah, so in theta you're considering theta as the set of parameters. So in that set of parameters, since z itself is a random variable following normal distribution, so those parameters, the mu and sigma, they will not be considered in theta.
No. It's fixed, no? Z is from normal 0, I, 0, 1. So that is fixed.
Okay.
The Z does not have any parameter. No, it's the input random variable. So typically what happens, no? We assume that we know how to sample from Z. We know, right? Because if you have, I mean, there are these functions called randn and random number generators in all these like programming languages, right? What do? They actually sample from a Gaussian distribution, correct? So we assume that we know how to sample from a Gaussian distribution, and therefore we can generate this Z as much as we want. And that has no parameters. What is parameterized is this function g theta of Z, okay, that this Z is passed through to get an x cap, okay, which has a distribution p theta.
Okay.
Is this okay? Yeah.
Yeah. Okay.
Okay. Yeah. Sachin?
Yeah, hi sir. This is the Gaussian distribution of this random variable z.
The random variable Z has a Gaussian distribution.
Okay. And sir, in this W3, can you scroll up a little bit?
Okay.
In this, sir, W3 will be a this matrix of L3 cross L2, right?
Thanks.
Okay. Yeah.
Typo.
Thanks.
Thanks. Vivek?
Sir, this the Z, did it, is it actually representative of the data, or was some transformation done to?
No. So Z is just an input random variable. Okay, it can be
Okay.
anything. You take it to be normally distributed.
Okay.
Typically, you take it to be normally distributed. It has nothing to do with data.
Okay, something was done to bring the data into Z form. I mean, like
No, nothing. It has nothing to do with data. I'm saying it has zero connection with data.
Data. Okay.
Yeah,
Fine.
it has nothing to do with data. Okay.
Okay.
So it is just that we are okay. So I'll tell you maybe the high level story, or maybe you just missed it. See, basically, what we are trying to do is we are trying to transform, okay, an arbitrary random variable to some random variable that has same distribution as our input data. Is that okay?
Right. Yes, sir.
Huh?
Yeah.
Now,
Yeah.
the Z is an arbitrary random variable, and we know that if you pass an arbitrary random variable through a function, the output random variable will have a different distribution. Now, the goal is to choose these parameters theta such that the transformation that this arbitrary random variable goes through will be such that the output random variable that you get will have the same distribution as that of input data.
Okay.
So now the goal is to set this g theta, set the parameters of the neural network such that distribution p theta matches with px. It means that I want the distribution of x cap to be same as the distribution of x, which is my input data. Z has nothing to do with the data. It is just an input seed. It is seed.
Okay.
It is the random seed that you start with. You pass it through a neural network, okay? And output of the neural network will have some distribution. I want the distribution of that output to match to the input, the distribution of given data.
Okay. Yes, in that case, the creation or the finding out of the distribution of Z is also as equally important as G theta of Z, right?
No, because
Or it is
yeah, it is just a random seed. No, you can start with any
okay,
distribution
anything.
because
Fine.
yeah.
Okay.
Hmm.
Nothing was done there, so we are just picking something, a random seed
Random
from.
seed.
No.
It
Okay.
is random seed. It is nothing but random seed.
Okay, fine.
Want to transform this normal distribution into distribution of interest via neural networks.
Okay. Yes, thank you.
Yeah, Astik.
Yeah, hi sir. So, in the last line, we discussed that the D should be greater than this K, but in a general neural network, generally like the model, the number of parameters increases, but in the last output that we are interested in, it is similar to that of input, right? So,
No, it is not
this,
input. No. In a classifier, what happens is the data will have a larger dimension, right? You give images and you reduce the dimensionality, and the final layer will be equal to the number of classes,
yeah,
right?
yeah,
Right? But in generative model, it is the other way around because the dimensionality of X cap here, the output, should be equal to the dimensionality of the input image because the final goal is to sample, isn't it? Now,
okay,
if you want to sample pictures of dimensionality 200 by 200 pixels, then the output of this neural network has to be of dimensions 200 cross 200.
okay. Okay, and what
You
would be
understand?
the input dimension in this case, if the image size is 200 cross 200?
Typically, it will be of size, let's say 16, 32, and so on. So that's why if you look at the shape of the neural network that I have written, it will have increasing dimensionality as you move deeper onto the network.
So how the input is like lower dimension in this example?
See, input is of 16 dimensions and you keep increasing. So, see, it is all in setting up this L1, L2, etc. Right? You choose. Those are the hyperparameters that are in your control as a designer.
Yeah, that is fine, but like our output should be a image and input is also a image, right? So,
No. It is not an image. It is a random seed. That is what I'm trying to say. Input is not an
okay,
image. So, this is a
okay.
generative model.
Okay. Yeah.
You understood the setup. It is not you are giving an image and you are asking for a class. You are inputting a random seed and you are expecting the neural network to give you an image from the data
Okay.
distribution.
Yeah. It's a generative scenario. Okay. Yeah.
So the course is deep generative modeling.
Yeah.
Just
Yeah.
joking. You
Thank you.
understood, no?
Yeah. Understood.
That's why the shape. Look at the shape, right? The shape of the neural network that I have drawn is that you start from a lower dimension and go to a higher dimension as you
Yeah.
move deeper into the
Understood.
network. Got it?
Yeah. Thank you.
Sushil?
Sir, I understand we are not using the input, but somewhere we will have to relate with the input distribution. Like, otherwise, how we will calculate the loss and all?
Come again?
Like, I understand we are not using the actual input here, but what I'm saying is how we will relate with the actual input distribution to calculate the loss.
I'm not saying that we are not using the input. I'm saying that the input distribution does not matter because you can start with any random seed and then convert that into distribution of interest using neural networks.
Okay, sir. So where we use the input here?
Okay. See, how do you get X cap here? X cap is gotten by taking a sample from Z, okay, and passing through. So basically, what you do in practice, I've written this, no, Z is sampled via random number generator, which means that you run rand n once, okay, you get one number, that is your Z. You pass that Z through this neural network Z theta, you get an X cap. That is how you use the input.
Sir, I was talking about actual input x1, x2 from the data set.
Oh, you mean, okay, so please don't call it as input, it's a little confusing. Input to this setup is Z, okay, and the data, okay, is X1 through Xn. everything that we do is using data. We will see that, right? I've not still
Okay.
told you how to set the parameters of g theta, right? The parameters of g theta is set by using the data.
Okay, sir.
I thought, I mean, yeah, I think, there is a confusion. Z is what is an input to this setup. Okay, and let us call let's call x1, x2, x3 as input, data. Okay, and this as the random seed. We will use, I mean, okay, let me, I mean, for everyone's sake, you know what I'm saying? When I say that the input distribution does not matter, I'm referring to this random seed, not to the data distribution. I mean, everything depends on data distribution because we are interested in modeling the data distribution. When I say input to this setup, which is the random seed, it does not matter if you sample from a normal distribution or you sample from a uniform distribution. Is that okay? Is this clear to all of you? I mean, that's a huge confusion if you had that confusion. Is this clear? Hello?
Yes, sir.
Yes.
Okay. Yeah, I think there's one more question. Sanchit?
Sir, I understand that we are just taking a random sample Z from the normal distribution and passing it through the neural network. We are getting X hat. Okay. But now, when we want to evaluate, like we want to compare this X hat, what are we taking it? What are we comparing it against? Like
I've
we are
not told you
saying,
that yet. I've not told you that yet. I'm just saying X hat has a distribution. Let's call it
okay,
P theta. That is what I've told you so far. I've not told you how to make this P theta close to Px. Anyway, because you're asking, I'm telling you. So evaluate the divergence between P theta and Px and set the parameters of this G theta such that that divergence is minimized.
sir, I understand that flow, like you had explained it in the last class. What I'm trying to relate to is, like, let's say for supervised learning, when we have the training data set, we pass, let's say we are going for
Okay, hold on. You are asking me how to do it practically, right? How do you, basically what you are saying is, how do you minimize the divergence practically, right?
yes, sir.
Yeah, I have not answered that question. Hold on. That is, well, I'll answer it in this class.
Okay, sir. Sure. Thank you.
Okay. Yeah. Harish?
Hello, sir. Sir, the sampling of the data, the normal distribution, no? So why do we consider it for a normal distribution, or can we consider with any other distribution? So for the Z
Yeah, you
here.
can. Yes, you can, but generally normal distribution is chosen because normal distribution has infinite support, no? Which means that like it has, I mean, for the entire space RD, the density function is not zero. If you take uniform distribution, for example, right, the density function vanishes out of, I mean, outside of a window. But in normal distribution, the density function is existing when it's non-zero over the entire space. No, that's why you take normal distribution.
I understand. And one more question on the dimension of K here. So the dimension K here, the dimension of Z.
Yeah, typically it is taken to be 16, 32, if you're working with images.
Okay. So does it matter? So you have mentioned that the D is much greater than K here, right? So does it matter based on the data size? So we choose 16 or 32, or is it also random?
Yeah, that's a good question. It's a hyperparameter, but in some of our research, we have actually found out that the dimensionality matters. Right, there is an optimal dimensionality is what we show in some of our papers. But yeah, in general, it's a hyperparameter.
Okay, and so we choose that once, like for example, we take an initial of 16 or 32, and then based on the training and how it works, so do we change that based on?
No, typically that is not a hyperparameter that people tune on. That is kept fixed. Okay. Yeah. Yeah. Nirmit?
So the real application of this function, I want to understand my assumption is correct or not. If we give some few text like a cup on table, then it will give me a picture of the cup on table.
Hold on. No. No. See, for now, I have not told you the conditional part of it. What you are saying is a conditional generative model. We'll come to that in a while. It is not conditional generative modeling right now. Right now, what happens is after you train it, you give a random number as an input to this. Okay, it will give you a picture from the distribution. Now that you are asking, let me just show you that as well. Yes. You see my screen, no? There is this website called thispersondoesnotexist.com. Okay.
Yeah.
So what is happening is every time I refresh this page, I get a new picture. You see?
Yes.
You see my screen, no? See, these are pictures of like non-existent people. So what is happening when I refresh the screen is that a random number is being generated, which is your Z, and that is getting passed through this network G theta, and you are getting a picture. Here there is no conditional generation. I'm not giving a text as an input. I'm just giving a random number as an input. Right now, I'm not looking at conditional generation. I'm simply looking at, this is called unconditional generation, where you generate images from the underlying distribution or generate data from the underlying distribution without conditioning.
Got it.
I will also talk of conditional generation, but you're skipping a lot. We will do that one step at a time. We will understand the unconditional part, and then adding conditioning is the trivial extension to this. Okay.
Yeah. So I know, sir, you have not explained this, but in the terms of picture, we got a p theta, but then how to measure like between p theta and px?
I've told you that I'll do this in this class. Please don't repeat the questions that I've answered already.
Yes.
That is the next thing that we will do. No, see, okay. So let me tell you my philosophy of teaching. When I teach, I just, like open it layer by layer. So now what is happening is I'm trying to give you an abstraction of what is happening. We will go to the details. So now at the level of abstraction, what you need to understand is that the idea is that you start with an arbitrary random variable z, pass it through a function g theta, and you get another random variable which has a distribution p theta. Now the next thing is you tweak the parameters of this g theta such that the distribution of the output of this network x cap, okay, is same as the distribution of px. Now, how do we do that is a question that I'll answer in a while. But now you ask me questions at this level of abstraction. Right? If you have difficulty in understanding this level of abstraction, sure, ask me questions. But things that I promised that I'm going to do in the due course, right? If you ask me that, anyway, I don't mind, but yeah, so just a request. Okay. Anyway, Mukesh.
Yeah, hello, sir. Sir, my question is regarding this dimensionality. Sir, in the CNN architecture, actually what we do, we try to implement this pooling layer where we try to reduce the dimensions of the data. But here we just passing the seed to increase the dimensionality. Is that correct?
Yeah. So the neural network here will have increasing dimensionality.
So actually here we don't have input data as an image. That's why we are trying to increase the dimensionality.
I would not say that. See, we want to start with some noise or some random arbitrary from an arbitrary random variable and generate images. So which means that we start with a lower dimensionality and we need to increase the dimensionality. Okay.
Yeah.
So now in terms, suppose, see, I have not told you that, see, this is not a CNN that I have written. What I have written here is a fully connected neural network. Okay, which is a feed-forward neural network or a multi-layer perceptron. If you want this to be implemented as a CNN, okay, that also has to be done in the TA session. So you have to teach about upsampling layers. So there are this neural network layers called upsampling, or they're also called transpose convolution layers. Okay, that will take as an input a lower dimensional feature and give you a higher dimensional feature vector as output. Just like you have convolutional layers, there are transpose convolutional layers that would increase the dimensionality of neural networks. Okay.
Okay, sir. Okay. Thank you.
But don't worry about architecture for now. I mean, for us, g theta is simply a function. I mean, it need not be a neural network also. But now, because in practice we are only looking at neural networks, I've said that it's a neural network. So for now, let us assume that these are all fully connected neural networks, which are, I mean, no fancy network architecture here, right? I mean, they are all multi-layer perceptrons or simply fully connected neural networks. Is that okay for
Yeah,
now?
yes, sir. Correct. Thank you.
Okay. Any other question? Is the problem setting clear to all of you? Okay. I didn't expect so many questions at this stage. Anyway, no problem. It's good that you're asking questions. Okay, let's move on. So now, what is the objective? So now the objective is to make p theta, okay, as close, okay, or make p theta close to px, correct? Now, if we do this, what happens is, suppose you are given data from, let's say, human face distribution. If we can have this setup and make my p theta close to px, then I have solved the problem of generative modeling. Do you agree? Every time I start with a random seed and pass it through g theta, I will get a picture from like human faces, because the distribution of the output of this neural network is now close to px. Clear? Is this clear? Okay. Now what do we have to do is that the question is that how to set the parameters of g theta such that p theta is close to px. This is the central question. Do you agree? So now, only thing that we have in our control is g theta, which are the parameters of neural networks. The question is, how do we set the parameters of neural networks such that p theta is close to px? We note that if you fix a value, excuse me. So if you fix a value for the parameters g theta, parameters of this neural network, you will get some distribution on some distribution on the output. Now, if you take another set of parameters, you will get another distribution. Now, the question that is to be asked is, which set of parameters of this neural network will ensure that p theta is close to px? Okay. Now, to do that is, the solution for this is that simply set the parameters of your neural networks such that it minimizes search over all possible sets of theta, such that some divergence between px and p theta is minimized. And this divergence now is a function of theta, right? Because if you choose a theta, you will have one set of divergence. So now what you have to do is that, so this means, write that down in English, that set the parameters of the neural network, okay, such that the divergence between px and p theta is minimized. That's the meaning of argmin. Okay. So choose a theta that would minimize the divergence between px and p theta. This is clear. Now the next question that comes up is, whatever you have been asking, question is, given data D. Okay. What is data? Remember that they are samples from Px. Okay. And samples from P theta. Samples from P theta. How do we have samples from P theta? They are simply the output of neural networks. Output of neural network G theta. See, output of neural network G theta is nothing but samples from P theta, right? Given data, which are samples of Px and samples from P theta, how to compute and minimize? To compute the divergence. This is the next question. You understand this, right? So now let me just tell you again. So in the setup, remember the setup. The setup is the following, that we have a neural network, G theta of Z, okay, and Z is a random seed from normal distribution, and we have samples from X cap, right? And this has a distribution P theta. We also have data that are some samples given, some images given from Px, okay? You should note that both Px and P theta are unknown. These two are unknown, but samples from Px and P theta are available. Okay, so you understand this, no? This is actually the most important thing, because this is the one that governs the entire like space of generative models, that you don't know the underlying distributions, but you have samples from those distributions. Samples from Px, the true data distribution is known because that is the data that we have. Okay, samples from P theta are also known because we can generate as many samples from P theta as we want. Because what do you mean by generating a sample from P theta? Let me just say, samples from Px is simply the data, given data, right? Given data D. Now samples from P theta, how do you get that?
Sampling.
Choosing different Z.
Correct. Choose different Zs and pass them through G theta of Z. You understand? So now we have samples from Px, samples from P theta. Now the question is, given samples from these two distributions, P theta and Px, how do we compute the divergence metric? And of course, why do we have to compute the divergence metric? Because only when we compute the divergence metric, we can minimize it, right? When we can use gradient descent or differentiate it and then optimize for it. First, we need to compute the divergence metric between Px and P theta. Given that we don't have access to Px and P theta, but we only have access to its samples. Now, 70% of this course will be answering this question in different ways. That given that we have samples from the true distribution and the generated data distribution, how do we compute a divergence metric between those two? Okay, so please try to appreciate and understand the problem. We have the distribution. Sorry. We don't have the distribution. We have the samples from it. So the entire statistics, right, and the machine learning and the other statistical fields, they ask this central question. The central question that is asked is that if you do not have distributions, but you have samples from it, how do you compute something? Now, in this case, we need to compute divergence metrics, right? In some other case, you might need to compute the moments, you might need to compute some integrals, etc., depending upon what the application is. But one of the central questions in statistics or probabilistic machine learning is that if you are given samples from distributions without giving the actual distributions, how do you compute some things involving the distribution? That is the central question. Now, in our case, what we should do, please don't forget the storyline. Storyline is that we are interested in generating samples from PX. Now, to generate samples from PX, what we have done is that we have taken an arbitrary random variable and we have a function g theta. Now, we know that passing an arbitrary random variable through a deterministic function will change the distribution of that function. Now, we need to set this function g theta such that the output of this function g theta will be a random variable that has the exact same distribution as that of the input data. Now, how do we do that? By minimizing the divergence metric. Okay. To minimize the divergence metric, we need to first compute the divergence metric. Now, the question now is that how do you compute the divergence metric between two distributions which are unknown, given that we have samples from them? Given data and samples from p theta, how to compute the underlying divergence metric? Is this clear so far? Any questions here? Okay, I see some hands raised. Karthik?
Yes, sir. Sir, I have a query. So we said about when we have samples of RK, then we get the sigma algebra using like L1, L2, all those parameters, right?
Hold on. I've never used the word sigma algebra here.
Sorry,
Where did I say sigma algebra?
Yeah, sigma of what we wrote, right?
That is a neural network. Okay, you start with a k-dimensional vector and you keep increasing the dimensionality till you go to d-dimensional vector. Yeah.
But so we don't have any control over whatever is written in RL1, RL2, other than our input, right? So these are fixed. That's what we are saying, right?
The dimensionality these are hyperparameters. No, L1, L2, L3 are hyperparameters that you fix.
Okay.
That you fix as a designer. So when you say, when people say that it's a billion parameter model, it is some 70 billion parameter model, what are they saying? They are referring to these L1, L2, L3. So that's a design choice.
Okay. Sorry, sir. What I wanted to know was whatever is the value of omega 1 or like omega 2. Those things are W1, W2, sorry. W1, W2. Those things are not in our control right away, right? Other than the.
No. Okay. Okay. So have you tried a neural network before?
In pictorial forms only, sir.
Okay.
I mean,
okay. See, how do you train a neural network? You start with some random initialization for the W1, W2, W3, W4. Okay. And then solve this optimization problem. You start with some W1, W2, W3, W4, and then you keep on changing these W1, W2, all these parameters till you reach a point where your objective is optimized. That's how you train neural networks.
So not just said we will be trying with various values. W1, W2 also like we can change.
All we change are W1, W2, W3, W4 only, no? That's the only thing that we would change, nothing else.
Okay, yeah.
When we solve this optimization problem that we have written here, what do you mean by optimizing over theta? Optimizing over theta actually means setting up these W's, no?
Okay. So
the
final changes will be in W1, W2, W3, W4. Only.
Right?
Whatever is the value.
Exactly of course, right? When you optimize over theta, you want theta star. What is theta? Theta is collection of all W1, W3, W3, all the parameters of the neural network. What you change are learning or training of a neural network is nothing but changing the parameters of it.
Okay.
That's why I'm asking you, right? Okay. Here is a small request. In next class, you please study about, what do you mean by training a neural network? I assume that all of you know what training a neural network is. See, I told you that the first 4 chapters of that Ian Goodfellow's machine learning book, deep learning book, is a prerequisite. Did you people go through it? Nirmit, did you go through it? Did you go through training a neural network, error backpropagation, and so on?
Just started. Like first 2 chapters are random process and linear algebra.
Okay.
I'm going through it.
Yeah. So please, quickly ramp up. See, now we have sort of come to the meat of the course. Okay. Like I expect all of you to know what training neural networks mean. Huh? So please go through those chapters, and that those are actually sort of very strict prerequisites. Otherwise, see, I can't teach how to like train a neural network in this course. You see. Huh?
Sure.
So please have a look at that. Okay, Vivek.
Sure. Thank you.
So when we look at the KL divergence formula, so because we are practically finding out the KL divergence between two distributions.
By the
But if
way,
you,
no. I mean, like, yeah, KL divergence is one of the multiple possible divergences. I will define now a family of divergence metrics. Okay,
okay,
that will be
okay,
minimized now. But anyway, you go on. Okay, KL divergence is one of
yeah,
them.
yeah. My question was, so you can you really in that formula it is like there is a closed form of two probability distributions, but
Correct.
in
You
this
don't know
setup that you
either
have
of them.
given,
No, even in KL divergence, see what is KL divergence between Px and P theta? Let me write that down. KL between Px and P theta is given by integral of Px evaluated at x log of Px evaluated at x divided by P theta evaluated at x. So to integrate this out, this is the definition of KL divergence, right?
right? Yes, sir.
Now you don't know Px, you don't know P theta.
Right. Yeah.
Right? How do we compute this? That is the whole question.
Yeah. Okay. Okay.
The whole question is that when we don't have underlying distribution density functions, but we only have samples from it, how do we compute the divergence metric is the whole question.
Yes. Yes. And also, the another question is, um, so any such metric, how can we have parallels for a single point for a single sample at a time? In the sense like,
No. None of the metrics, none of these metrics are doing. I mean, like they are point wise.
okay, they're
You
like a
need
group
the,
of examples, a
we
group
will
of
see. No,
pictures.
I have
Okay. Okay. Okay.
a group of pictures.
Okay.
See, how do you compute these divergences when you don't have distributions and only have samples is a question that I have not answered it. I will answer it in a while.
Okay.
If you have questions on the setup, ask me. Okay, so these are things that I'll discuss in a while. So any questions on the setup?
Okay. No.
Okay. Yeah. Avirup?
Yes, sir. I have a question on the last statement. So, samples from P theta choose different Zs and pass them through G theta. Now, Z is a random variable which you are passing through a neural network. So, my question is, why do we have to pass different Zs, random variable being a function, if we pass a different point belonging to the range space of the random?
Yes, that is what we do. When we say different Zs, that's exactly what we mean. You sample from the range space of the random variable and then pass. Always that. See, whenever I say that they are points from random variable, they always mean that it's from the range space of the random variable.
Yeah,
Always.
Okay. So, you have written.
I think we settled this in the first class itself, right? I told you that I say that when I say that we have n samples from a random variable, I said that I always mean that there are n samples in the range space of the random variable with a distribution. I think that we have settled, no?
Yeah, that is settled. I thought that since you've written choose different Zs, I thought you were choosing a different random variable altogether.
No,
Anyway, sorry.
no.
Okay. Yeah.
No, yeah. Okay. Is that okay? Shall we move on?
Yes.
Okay, so now the important question is, right, how do we compute this divergence metric when we don't have distributions but only have samples from it? Okay, before we take that question, let us. By the way, I will tell you the answer is through this adversarial optimization. This entire generative adversarial network, right, or adversarial optimization, it is asking, it is trying to answer this question, which is that how do we compute the divergence metric between distributions and we do not know the distributions, but only have samples from it. This adversarial optimization is one way to do it, by the way, and like variational inference is one other way, which will give rise to VAEs and diffusion models. Okay, so adversarial optimization is one way, the variational inference is one other way, and MMD is one other way, and so on. We will look at different ways of doing it. A maximum likelihood estimation is one other way, which is what is used in the LLMs and so on. We will look at all possible ones one by one. Okay, that is what we do it in this course. We do in this course. Okay, so let us look at adversarial optimization. For that, let's take a okay. Now let us define a family of divergence metric first. This method now that we will look at right now is powerful enough to be able to handle a large class of divergence metrics. Okay, it's a common thing. Okay, or rather, it's a method that would enable minimizing the family of divergence metrics. Not one divergence metric. It will enable us to minimize a family of divergence metrics. Okay. Now, for that, let us first define a family of divergence metrics. So, given two distributions, given two probability distributions, let me just work with the density functions. Given two density functions, px and p theta. Okay. Define a divergence I've already seen one divergence metric, no, in the last class, which was the Hilbert-Leiber divergence. I will define a large class of family of divergence metrics. Okay, all of that can be minimized using the technique that we will see in this class. Okay, that's why I'm defining a large class of family of divergence metric. Given to density function px and p theta, define a divergence metric as follows. Define that as df between px and p theta is defined as integral p theta of x f of px of x divided by p theta of x dx. This is the definition of f divergence, where f of u is a function that takes a positive real number and maps it to another positive real number. It is a convex function. I will explain it in a while. Okay, so these are called f divergences. Okay, so let me explain what this is. Now, suppose we are given two density functions and we want to define a divergence metric between them. What is a divergence metric? Remember that it will give you a sense of distance between two density functions, right? Now, there is a class of density functions that you can define, which are called f divergences, which is defined like this. So this is the definition of f divergence. Okay, what is it? It is you take it is integral p theta of x f of px by p theta of x dx. Okay, let us look at this this term that is inside this bracket. Now you know that the density function px of x is a scalar, correct? density function is a scalar valued function in the sense that it will take a vector x and it will give you a number, a positive real number, right? So all of you know this, right? What is a density function? Density function is a scalar valued function. Okay. So now if you evaluate the density function px at some x, you will get a scalar. And if you evaluate the density function p theta of x, you will get another scalar. So ratio of these two, px by p theta at a given point x is a scalar. Correct? Now this function f, okay, of u takes a positive real number because the ratio of these two density functions is a scalar. It takes a positive real number and gives you another real number r. That is this value. F of this ratio is this value, and the definition of f divergence is the integral of p theta of x, okay, times f of px of x by p theta of x dx integrated over all values of x. This is the definition of what is called. It says got muted. This is the definition of what is called as an f divergence. Now you can choose an f function. Okay, I'll give you examples. So now if f of u is of u is a, what is u here? U is px by p theta of x. Okay, it's a scalar. Here I've just written that as a dummy variable u, but in the definition it is the ratio of the density functions. If f of u is equal to log u, okay, then the corresponding divergence is called the KL divergence. Okay, now if f of u is equal to, let's give you some examples of it. Sorry, it is u log u. Sorry, if it's u log u, then it is that. If it's half of u log u minus u plus 1 log u plus 1 by 2, okay, this is called the Jensen-Shannon divergence. Okay, if it's half mod u minus 1, then this divergence is called the total variation distance. And so on. Okay, so now you can choose any convex function for this f, and one choice for this convex function will give you one divergence metric. So basically what I'm doing is I'm defining a family of divergence metric, okay, which is like one of the, I mean, you can choose a convex function and you get one family of one divergence metric. Now what do you mean by this? If I write u log u here, what will happen to f divergence? Let me show you that. Example, okay. Now f divergence is given as integral p theta of x log of, sorry, f of px of x divided by p theta of x dx, correct? Now let us say that f of u is u log u, okay. Now in that case, df will now become integral p theta of x to substitute u log u for f of u, which is now this entire thing, which is right inside this f, is now called as u. This is p of x px of x by p theta of x. This is u, correct, into log of u px of x divided by p theta of x. Note that this entire thing which I have written is f of px of x by p theta of x, correct? This is what it is, to dx. Now I will skip the algebra, okay? So if you simply this is A times log ratio, right? So now you just take the ratio inside and so this, okay, so this p theta x and this p theta x cancels. This will be px of x times log of px of x divided by p theta of x dx, okay, which is nothing but the Kl divergence. Understood? That's what it is, right? So what we are doing is that we are defining a general family of divergence metrics. Now, if you take where these are called F divergences. If you take some form for this F function that is there in the definition of F divergence, you will get different divergences. You get Kl divergence with one F. You will get Jensen-Shannon divergence with one other F. You will get total variation distance with one other F, and so on. So basically, we are defining an infinite family of divergence metric between two distributions, depending upon what your F function is. The reason I did it is what is the coherence or relevance to this is that the adversarial optimization technique that we see, you look at what we are doing, right? We want to now minimize or compute the divergence metric given samples from two distributions, right? Now, what divergence metric are we considering? We are considering not one divergence metric. We will be giving you a tool or a technique that would compute and minimize a family of divergence metrics that are called F divergences. You can choose any divergence. See, if you people know this generative adversarial networks or GANs, when after this paper came, there are so many improvisations that came over it. No, that's called like LS GAN, X squared GAN, like there is some W GAN, this GAN, that GAN, all that. They are nothing but changing this F divergence. That's all. So you take one definition for the F divergence, you will get one GAN. So what we will see right now is we will not look at minimizing one divergence metric. We will now look at minimizing a family of divergence metric given samples from the underlying data distribution. Is this clear? So now, any questions on the definition of F divergence? So basically, what we need is given some convex function F, a scalar valued convex function F, we can define a divergence metric between pair of distributions. Okay, and Kl divergence happen to be a special case of this, and Jensen-Shannon divergence happen to be a special case of it, and total variation distance will happen to be a special case of it, and so on. So there's a lot of very, very well known divergence metric. It are all special cases of these F divergences. Okay, in general, at an abstraction level, this is, you think of it like the definition of a class, right? I mean, where each of these divergences are one instance of this class of divergences called F divergences. What we will see now is that given the samples from the underlying distributions, how do we minimize any F divergence between those two using samples? Let me write that down. Now the objective is, I'll take questions in a while. Cool. Compute F divergence, okay, between Px and P theta, okay, using their samples. Without knowing what Px and P theta are. Right? We don't know Px and P theta, but we have samples from Px and P theta. Now, how do you compute the F divergences between them? Is the next question that we will answer. Okay, any questions here?
Yes,
Shivam? Go on.
yes, sir. Yes, sir. On the F divergence side, as you have said, we can have infinite combinations of F divergence function. And
Not combinations. No, there are no combinations here. We can have infinite F divergences by changing F.
yes. Yes. So, yeah, but we are talking about the three variations, the KL divergence, GS divergence. So is there any specific benefit does they bring into the table, or
Good question. Yes, they do. They do. In fact, after we look at how to minimize this, no, I will tell you like advantages and disadvantages of, let's say, at least scale and Jensen channel divergence. Okay. But yeah, so different divergences have different properties. That's a good point that you made. Why do we need so many divergence metric? Why can't we look at one of them? Is because different divergence metric offer different properties. I will talk about it, right? I mean, just after we look at this algorithm, right? Remind me, Shivam, okay, if I forget it, just remind me to bring out the, let's say, properties of at least one or two divergences here.
Sure, sir. Thank you.
Okay? But yeah, so that's the point. I mean, why do we need so many divergences? In fact, if you come up with a different divergence which has good properties, no, you can name it Shivam divergence. That's how people have done it. They have, I mean, different people have come up with different divergences and called them with their own name. Okay, but you'll have to ensure that these things are there, right? I mean, you'll have to ensure that this is a convex function. To be mathematically precise, this is actually a left semi-continuous function. Okay, the left semi-continuous function, and also f of 0 has to be equal to 1. The convex left semi-continuous function with f of 0 equal to 1. So if you can come up with such a function, that becomes a new divergence metric. And if it has favorable properties, you can use that in your generative models. Yeah.
So why should the function be convex? Yeah, I mean, we know that, but it's just that it should be when you do argmin, is it? Like
no, we're not doing argmin here, anything, right? I mean, it is
optimization.
We do optimization over df. We minimize the divergence metric. No, we don't. We have nothing to do with f. F is actually a hyperparameter, right? You fix f. Yeah.
Okay.
We choose an f divergence. It has nothing to do with the optimization. It is just the definition of the f divergence. Huh? Any other question here? See, in practice, what we do is that we actually fix an f. I mean, for instance, in the naive vanilla GAN paper, right? They choose this f to be equal to this particular f. I wrote it, no? This particular f. This thing is what they do in the naive vanilla GAN. They take Jensen channel divergence in the vanilla generative adversarial network. They choose this f to be equal to this particular form, and what they minimize is the Jensen channel divergence. Okay, you choose it. You actually fix it. You fix that. F divergence, and then compute and minimize to find a sample. Is that okay? Hello? Am I there?
Yes.
Hello, can you hear me?
Yes.
Okay. Okay. Any other question on the definition of divergence? This needs an uninterrupted to answer this question, right? We need 40-45 minutes of uninterrupted time. Maybe let's just take a break and then get back. Shall we? Let's take a break now. Huh? It's 10:55 in my clock. Let's resume at 11:15. See you in about 15-20 minutes. Hello, shall we resume?
Yes, sir.
One of the most challenging parts of this online teaching is that I don't get to see you at all, right? I mean, all I get to see is this stupid screen. And as a teacher, I've been we would have developed this ability to look at the face of your audience and kind of mostly discern what is going on. I mean, are they appreciating what you are saying? Are they understanding what is said? You know when to repeat, you know when to stop, when not to repeat, etc. The complete feedback mechanism is gone. Here it is only me talking, don't even know whether you people exist or not. Yeah, it's such a challenging thing to do that online. Anyway, okay, I see a couple of hands raised. Yeah, Astik.
Yeah, sir. So you mentioned some properties about this f function for f divergences. Can you move a
Correct.
little up?
Yeah, it should be convex, lower semi-continuous, and at 0 it should evaluate to 1.
But this is not following in this these three functions that we write, right? This
Is it?
f0 is equal to.
Hold on, I think I just. Thanks for
It
that.
should be, I think, f1 is equal to
F1
0,
and
right?
0. Correct, correct. Yeah, thanks.
Yeah.
Proofed up. Correct. It's correct. It should evaluate to 0 at 1. Correct. Thanks.
Okay. Yeah.
Okay, shall we continue?
Yeah, sure.
Okay. See, as I said, no, the goal is now to compute this divergence between a pair of distributions when the distribution is unknown, the samples are given. So here is the overall philosophy of how it is done. As I said, no, this is a recurrent theme that comes up in almost all the ML models. How is it done is the following. Now, observe that these F divergences, right, or any divergence metric, now involves, let me not write the so suppose you have, let's say, an integral, okay? You need to compute an integral of, let's say, some function, running out of alphabets. Let's just taken B is taken H, okay, let's take some function H with respect to some probability density px, okay? If this integral has to be evaluated, okay? Now let's say that you need to evaluate this integral, evaluate this, okay, with px unknown, okay, but have samples from px. Okay, now suppose you need to evaluate this sort of an integral, okay, where h is some function, h of x is some function, any function, okay, some function of x. So you have some function of x, and you need to evaluate this integral with px unknown. So if you don't know px, then you cannot, of course, integrate this out, right? Now, one statistical tool that can be used to do this approximately, of course, you can't evaluate it exactly because you don't know what px is, but it can be approximated. How? There is this nice theorem called law of large numbers that would say, okay, law of large numbers says the following. Suppose x1, x2 up to xn, okay, are sampled from some px. Okay, then to compute some, okay, then integral h of x px dx, okay, can be approximated by limit of 1 by n, I is 1 through n, okay, h that is evaluated xi, where xi are samples from px. This is a very strong and powerful result. What are we saying here? Please note this. Now, as n goes to infinity, we are saying, suppose you have lots of samples drawn from a distribution. Okay, then if you want to compute this sort of an integral, that can be approximated simply by taking the sample mean of all these functions. I mean, the sample mean of the function values evaluated at all those xi's coming from px. Now, a special case of this is maybe something that all of you know, right? If h of x is simply equal to x, then what happens? Then what is this? What is this thing called? This is
Expectation.
This is the expectation of
X.
this is the expectation of x, right? Now, in fact, this is the expectation of h of x with respect to this density px. Okay, this is the definition. Now, this is the expectation of x with respect to px. Now, this can be approximated using this. All of you know, no? This is what we do in practice, isn't it? If you want to know the expectation of a distribution, you just take the sample mean. What is this? This is the sample mean. Sample mean approximates the true expectation asymptotically, which means if n is n goes to infinity, if you have enough number of samples, then sample mean can be approximated. Sorry, the true expectation can be approximated using sample means. All of you know this, right? This is called law of large numbers. Any questions on this? Hello, am I audible? Okay. Now, yeah. So basically, what did I say here? That you don't have. What did we do here? Look at this. No, we have integrals. I mean, this integral is nothing but the expectation of the definition. No, this is the expectation of some function h of x with respect to px. If you want to compute the expectation of a function with respect to some distribution, okay, without knowing the distribution, but you have samples from it, you can invoke law of large numbers and simply compute the sample average, okay, over all the samples that are coming from the distribution. See, please note this very carefully. While we do not know what the distribution px is, we have samples from them. That is exactly the scenario that we have right now with us, no? We have samples from the distributions, we don't have the distributions. But in spite of not having the distribution, we can evaluate expectations of functions of random variables with respect to the underlying distribution using sample averages. Is this clear? Is this idea clear? Okay. Now, let's come back to what we had in our mind. So we want to minimize the F divergence. We want to compute the F divergence. Now, let me connect the dots. If I can express the F divergence, let me write that. If F divergence can be expressed in terms of expectations over px and p theta, then df can be computed using samples from using the word using two times via law of large numbers. Okay, what am I saying is we want to compute the F divergence between pair of distributions. We don't know what the underlying distributions are, but we have the samples from it. Now we also have this nice result called law of large numbers that would say that the expectations of some functions with respect to some in underlying distributions can be computed using sample averages if we have samples from it. That's what law of large numbers says. Now connect these two, that if we can somehow express the F divergence or the quantity that we want to compute in terms of expectations over Px and P theta, then we can use law of large numbers and approximate the F divergences. Do you agree? That is exactly what we will do now. Now the goal is to express F divergence, okay, in terms of expectations for Px and P theta. Okay, that's what we will do. Now, unfortunately, what happens is this is not possible. You can't express the F divergence or any divergence metric in terms of expectations over Px and P theta. Okay. However, we can express bounds on F divergence using expectations. So let me write that. Okay, so what am I saying? I mean, F divergence cannot directly be expressed as expectations over this, but we can express lower bounds on F divergences in terms of expectations. What do you mean by lower bound? We'll compute a quantity, okay, which is always greater than or equal to F divergence, okay? Then this quantity can be expressed in terms of expectations, expectations over Px and P theta, okay, and then remember that finally we want to find a g theta, okay, or our generator function such that this F divergence is minimized, right? Now, because we cannot compute the F divergence, what we do is we carve a lower bound on the F divergence, which can be computed, and we minimize this lower bound instead. Does it make sense? But that's not an exact thing, right? I mean, it would have been great if we can actually minimize the F divergence itself. But we cannot minimize the F divergence directly because F divergence cannot be computed without knowing the distributions. Now, what do? Instead of minimizing the F divergence, we minimize a lower bound on that. Okay, we minimize a lower bound, rather we minimize a quantity that is always greater than the F divergence, right? Yeah, the F divergence, we minimize a lower bound on F divergence, and that lower bound can be expressed in terms of expectations over Px and P theta. Is this clear? Any questions on this? See, these are very, very critical and important stuff, okay, which is, again, as I said, this is a recurrent theme that would keep coming. So if you have questions here, do ask me. I'll wait for a minute. Now this implies that instead of minimizing F divergence, we minimize the lower bound. Any questions on this? So don't ask me how do we do it. That is what we will see. But yeah, on the philosophy, yeah. Somebody?
Sir,
Somebody
that
else
will
talk.
be an approximation, right? Like,
Correct. That will be an approximation, but unfortunately, that's the best that we can do. Because you know that like the fundamental problem is that we don't have access to px and p theta, you see. Since we do not have access to px and p theta, this is the best that we can do. But yeah, what you said is true. It's an approximation. You will not get the correct minimization of F divergence.
okay, sir.
Any other, yeah, Lokesh?
Yeah, sir. So if we are minimizing the lower bound, does that mean it does not mean that if you have a lesser lower bound, one model is better than the other, right?
Correct.
It's
That
only
is
the
true.
lower bound that we are.
Correct. That is correct. That is why, it's better. That's very good question, actually. That is why we need a tighter lower bound. Right? I mean, the tighter the bound is, the better your model is. We will crave to have a tighter lower bound. See, if you know what a GAN is, right? Generative adversarial network, you will have two networks there, right? One is the generator network that we already wrote. There will be another network called discriminator network. Are you aware of it?
Yeah.
See, that is actually to carve this lower bound. We will see that in a while. So, why do we say that the discriminator has to be very good? Is because the lower bound that we compute has to be very tight. Otherwise, it doesn't. I mean, it will be a very loose approximation, which will not lead to a good generative model.
Okay.
Yeah, but this is the best that we can do. Why? I mean, why is this problem arising? Is because we don't know px and p theta. Since we do not have px and p theta, we need to do something, right? What do? We'll carve out a lower bound on F divergence and then minimize that. Now, this lower bound can be computed using the expectations over. Using the samples of px and p theta. That's the point.
So the lower bound is in terms of, is for the term EPX minus EP theta, right?
It will take that form. It will take that form of like differences in expectations. That is what we're going to show now.
Okay.
That's the whole result. The lower bound that we carve now, that can be expressed in terms of expectations over these two distributions that we had. And excuse me, once we express them as expectations, right, over these two distributions, we can compute that using samples.
Yeah.
Make sense? Yeah. Any other question?
Yes, sir. Sir, if we don't know px and p theta, as you have said, we know the samples from it, and on the above you have applied law of large number to find the expectations using the samples. So why can't we just directly apply into KL into while we calculate divergence? Like we can apply the same tactic while finding the divergence as well, right?
That's what I'm saying. These divergences, for instance, if you take this some like Jensen channel divergence, right? You can't express that in terms of expectations. If you can express that in terms of expectations, then great, but you can't. The whole point is that you can't write this F divergence, this F divergence, right? Is that this definition of F divergence in terms of expectations over P theta and Px. If you can, then that's it. I mean, it's an exact computation, but you cannot represent that. That's the problem. Because of that, you need to do something. What do? We carve a lower bound on F divergence, which can be represented as expectations, right? Which can be computed. Yeah, that's the whole point. Understand that?
So just a small extension. So we can't do it because it's not a h of x, right? But it's depend, because if you see the form, it is very similar to expectations.
Not necessarily. No, you have f. See, it is not. See, h of x, right? It is not h of p of x. You see, this entire thing. Yeah. So there are ratios of densities here, right? This is not equal to, for instance, expectation of f of that with respect to p theta. This is not equal to that. Understand?
Yeah, because it itself depends on the p end.
Yeah,
Px
f
and p
itself
theta.
has a dependence on px and p theta. It is
Yeah,
not equal
okay.
to the expectation, right? We need
Yep.
to do something else to write it as an expectation of functions over these two distributions. The way to do it is to carve a lower bound on it and then express that as expectation which can be computed.
Yeah, got it.
Huh? Anything else? Anybody else? Okay. Now, yeah, as I said, no, the classes now will get a little denser. So please focus and as much as possible and remember what's going on. Otherwise, it's very easy to get lost. I mean, there are too many things that we will do, right? I mean, unless you know what the storyline is, you will kind of lose the track. Please focus. Okay, so now what should we do? We should now carve a lower bound, right? Or let me write that expressing bounding df and expressing it in terms of expectations. Expectations. Okay, this is what we will do now. Okay. Let us start from the definition of f divergence. F divergence between x and p theta given as integral p theta of x f computed at ratio of px and p theta px. Okay, this is the definition of divergence. Now, okay, to do this, we'll have to know what is called as a conjugate of a convex function. Okay. Now remember what we are doing. We are trying to bound the f divergence and express it in terms of expectations. To do this, we'll start with what is called as the conjugate of convex function. Now, the thing is, if f is a convex function, let me call it f of u because it is a scalar valued function that we are talking about here, right? In the f divergence convex function, there exists convex conjugate. Convex conjugate function f star of t. Note that both u and t are dummy variables, okay? Simply some variables. Star of t defined as follows. F star of t at a point t is given as the maximum of ut minus f of u okay? This maximum is over u, which is the domain of f. I will explain what this is. What we are saying is that every convex function f, okay, has what is called as a convex conjugate. Okay. Now, what is convex conjugate? It is another function f star of t. Okay, that is defined this way. F star of t is simply f star of t at t is simply the maximum of ut minus f of u where u comes from domain of f. What does that mean? Let me just draw it and show you. Let's say that you have some convex function. Let us call this f of u. This is a convex function, right? And this is axis is that this is the u axis and this is f of u. Okay. Now, let's say that you take a point here, some point on the u axis. Let me call this u. Okay. Now, what I can do is I can construct, I can write multiple lines, okay, all of which are less than f of u at that point. Do you agree? So given a convex function, okay, I take a value of that convex function at a point. I can construct infinite number of lines, okay, I can draw infinite number of lines that lie below that point, okay, for all u. Do you agree? Okay, so out of those all, I mean, there are infinite lines that I can draw, right? Out of all those lines, there is also this line which is the tangent. There is also the tangent, okay, that is equal to the value of that function at that particular point, okay. Now, this point, right? I mean, the intersection of that tangent and this particular curve is what I've called as maximum here. Look at this, ut minus f of u, okay, for different values of t represent, okay, different values of u, different values of t represent all these lines that I can write at every point of the convex function. Let us take one point, for instance. If I take one point of this convex function, there are multiple lines that I can draw to this curve at that particular point, which is represented by this family of lines. Now, amongst all these possible lines, okay, if you take the maximum value of all these possible lines at that particular value of u, what do you get? It's actually the value of that tangent of to that function at that point. That is the value of that convex conjugate at that t. You get it?
Sir, one question.
It's actually not the tangent, right? It's actually the slope at that particular point. Now, if you collate all these at different points of view, you get another function, right? It's a collection of slope of this function at all points. That becomes the convex conjugate.
Sir, one question.
Yeah.
Sir, it's basically the function value f of u, right? Even if we are getting that through the tangent, the maximum value will be f of u only.
No, maximum of ut minus f of u. That's what I'm saying. Not f of u.
Okay, no, you were explaining about this this concept, right? Like we can have infinitely possible lines at a particular u. One of them will be
that are less than this at all points, right?
Correct.
That are less than that at all points. So now I'm considering out of all of those possible lines, I'm considering the one that has the maximum value of that particular u, and that I'm considering as the value of that conjugate function at that particular t.
So that value is corresponding to f star of t, like that.
That is the value of correct. That is the value of f star of t at that particular point. See, ut, I mean, f of u, what does ut minus f of u represent? The f of u minus f of u, right? This f of u is the, no, something happened. Yeah, hold on. This f of u is the intercept, right? At a given point, this f of u, this is like mx plus c, isn't it?
Yes, sir.
This is the intercept, okay? Now, you see, I mean, t is the slope and u is the value of the domain at that point. So basically, ut minus f of u will give you a line. At any f of u, ut minus f of u will give you a line, okay, whose intercept is f of u. Correct?
Okay.
Now I'm saying out of all these possible lines, okay, that are less than the function value at that particular point, I'm looking at that line, okay, which is maximum.
Okay.
Do you understand? Now, yeah.
So it lead to one confusion, that the distance should be minimum, right? Like the value at f of u and ut minus f of u, the line which you have, it should be very close to f of u to get a tighter bond, right? So it should be, the line should be the minimum of it.
So the maximum of the value, no, the maximum value of that function. See, we are looking at the value of this function itself. So this ut minus f of u is a value that evaluates to something. So you're looking at the maximum of that. And the maximization is over all possible u. See, the optimization is over the u domain. You look at all possible u's here. Okay, so amongst all possible u's, you look at that u which will maximize this entire thing ut minus f of u. Fix a t, okay, fix a t. So what do you mean by fixing a t? See, you can see t as the slope, okay. You see t as the slope. You fix a slope. You see, you fix a particular slope. Maybe the way I have written the figure has a different interpretation. Okay, let me rewrite it. Hold on. Let's make it more inclusive. Is it not moving? Okay. Just let me draw a convex function. This is a convex function. Let us take one particular u. Okay. Now here, draw the axis. Okay. T is the slope and f of u is the intercept, right? Minus f of u is the intercept. So this is f of u. So minus f of u should come the other side. That is the intercept. Okay. Now, you are looking at maximum with respect to u. If such the function, t is the slope. Now this is, you can write this is 1t, okay. If that as the intercept, you can write go through that now. There's another line and this is straight lines. There's another line. There's another line and so on. These are the lines that we are talking about. Is this clear? I think now it is correct.
Yes, sir. Yes. Sense.
Correct?
Yeah.
These are used. Correct?
Yes,
Now,
sir.
amongst all these possible lines, I am looking at that particular line, okay, which would maximize that at that u. So this is the u that we are talking about. Okay, so amongst all possible lines, okay, that would be a lower bound for this function at that particular u. I am looking at that line which would maximize the this value ut minus f of u. Is that clear?
Yes, sir. Yes, sir. Now clear.
By the way, it may not be a tangent. Oh, the all times it may not be the tangent. Okay. So this, okay,
Yes.
so you're not seeing the entire picture. So these are multiple lower bounds that are possible for the convex function at that particular value. Amongst all possible lower bounds, we are looking at that possible line, okay, that would maximize this. All of you clear on this? Any questions?
Sorry, the quantity which we are maximizing, can you show it on graph? Possible?
U is fixed. U is fixed. So
No,
the
ut
value
minus
of
f of u.
yeah,
The whole
ut minus f of u is the line, no? This is one ut minus f of u. Let's call this t1. This is like u t2 minus f of u and so on, right? Amongst all possible lines, no, we are taking that line which has the maximum value at that u, at u. See, at u, this line has this particular value, right? At u, this line has this particular value and so on. I can construct more such lines, no? Which becomes lower bound. I can construct another line. You understood, right? Different lines have different values at that u. So now amongst all possible lines, I am taking that line, okay, which has maximum value, and the value of that line at that particular u happens to be the value of the conjugate at that t. Yeah, does it make sense now?
Yeah.
So is it the value of u that maximizes u of t
Different
minus f of
values
u?
Correct. The
Or
maximization is over domain
for a
of u.
given
Domain of
for a
f.
given of
For a given
for a
t.
for a given value of t, right?
Correct. Correct.
So you choose a t and then find the maximum from u. Find the u that maximizes ut minus f of u.
That would be the value of f star of t at that particular
Okay.
u.
Okay.
It's a point-wise definition. Make sense?
Yes.
So this has nothing to do with divergences or anything. This is just a definition of a convex conjugate of any convex function. This is true for any convex function. Okay. It's also called the Fenchel conjugate. Basically, the definition of a conjugate function. Okay. Shall we move on? Okay. Now this has to be taught in a convex optimization course, but it's okay. Whatever we need, we will do it. So now, so there is a property that would say that f star, I'll state this without proof, f star is also convex. F star is also convex. And so, okay, so first of all, we say that f star is also convex. If f star is also convex, this implies that you can take the conjugate of the conjugate, right? Because f star is conjugate. Now we know that every convex function has a conjugate, which means that the conjugate also has a conjugate. And there's a property that would say that the double conjugation of the function will take you to the original function. So this is another property that we will use. Okay. So two things. One, f star is also convex, which means that that also has a conjugate and that will take you back to the original function. Okay. Now this implies that we have the original, okay, so f of t was the conjugate for f of u, right? Let me write that maybe. ut minus f of u, and this is over u, right? So now this is the f star of t. This is the conjugate for f. right? Now we can take a conjugate of the conjugate. F star of t, you take the conjugate of the conjugate. What is this? This is equal to f of u, we know that, okay? So conjugate of conjugate, how do you write that? It is simply to take the domain of the conjugate, okay, and subtract it with its conjugate, which is, subtract it with its value, and this maximization is over t, which is domain of f star. Do you agree? Simply taking conjugate of the conjugate. What is the conjugate of the conjugate? Conjugate is also convex. So this is the conjugate of conjugate. This is the conjugate of conjugate. We know that that is equal to the original function f. That's why f of u is equal to maximum over this. Questions on this? Do you agree? See, I have just replaced f of u with f star of u because f star of u is another convex function, right? We can write conjugate for any convex function. F star is another convex function. So I will write a conjugate for f star as well, which is this. It is this. And this we know that if you take the conjugate of conjugate, you get the original function. Is this clear to all of you? Okay. Okay. So now, okay, why do we need this? Let's come back to our definition of our F divergence. Remember that we are looking at bounding this F divergence. Okay. Now this is integral right? So this is, let me call this as f of u dx, okay, where u is, sorry, I think I wrote it incorrectly. This should be p theta. Okay. Now if it is a convex function, which means that this f now I can replace this and
Sir,
if I use this, yeah.
Sir, either the initial one should have px or the last one should have px, because once we replace,
I didn't follow. P theta x times f of px by p theta, right? That's the definition.
once we replace px by p theta
Oh,
with
we
u,
haven't, right?
so
Just called it as this ratio. I called as u. That's all.
okay.
It's a scalar. No, I just called it as a scalar u, f of u.
Okay. Okay.
Nothing complicated, right? I just am representing it as some scalar, right?
Yes, sir. Yes, no issues.
Now, f of u, we have this result, right? Can be written as max of pu minus f star of t. Maximization is over t, correct? This is what we have written here. Correct? I will use that there, which means that my f divergence now can be written as the integral times max of t, okay? What, okay, I'll write it as pu minus f star of t dx. Maximization is over t. Agreed? What did I do? I just simply replaced f of u with the definition, okay, by using the conjugate of conjugate property. So if you agree, This is another problem with this online teaching, that the screen is so small, right? I mean, I need a large board where, see, imagine I would have written this somewhere else, no, you would have had the view of this. Now you can appreciate that since I have written f of u using this max thing, all I have done is I have replaced this f of u using this, using this definition. Is it okay? Questions,
Yes, sir.
right? Okay. Now I'll just expand this. This is integral p theta of x over t. Now t times what is u? U is ratio of px by p theta minus star of t. Correct? Correct? Yeah. Now look at these terms. Look at these terms. Okay, I'll write it as t times this. Now look at these terms. If I can somehow take this max out of the integral, okay? If I take the max term out of the integral, what will happen? Can somebody tell me what will happen? If I take max, if I take max out of the integral, then it will be t times px minus the integral of, so it will be like this, no? Somehow take the max outside, okay? It will be integral p theta would cancel out. It would be t times px of x dx, correct? Minus integral f star of t times p theta of x, correct? Do you agree? Can you see that?
So can we take the max out?
Yeah, hold on. I'm just saying, if you can, I mean, you can't, I will tell you what happens if you take the max out. But if you can, let's say, right, then it will become like this. Now, this is an expectation, right, over px. And this is an expectation over p theta. You understand that? That's all. Now, all this exercise that we did, right, in representing the f function using its conjugate, all that was to ensure that we can somehow express these in terms of expectations. Now we are almost there. We just have to somehow push this max out. And if we can push this max out, then we achieve whatever we want, that we can write our f divergence in terms of differences in expectations over px and p theta, which we know how to compute. Can you see the point? Now the question is, how can you take the max out? Right? So max is over t. How can you take the max out is the question. That needs, I need some half an hour to complete this proof now. What shall we do? We have
Sir, we have time until 12:15.
12:15, 10 more minutes.
Yes, sir.
10 minutes might be lesser to do this. Anyway, I will quickly run through it and do it again in the next class, perhaps. Okay. Any questions so far? Does anyone have any question? Okay, no. Okay. Now, okay, so let us observe this entire thing. Okay, so this is a maximization over T. Can you see that? This is a maximization over T. Okay. However, okay. So let us call this maximization over. Okay, maximization of. Let me say that of an objective function. Okay. objective function. Let me call that function as capital T, okay, of a function T over T. Do you agree? So this, whatever I have marked using floor bracket, right? It is a maximization that you are that an optimization that you are solving over T as the variable. And if I call that entire function that you are optimizing using capital T, okay, then it's you are maximizing capital T over the variable small t. Do you agree? Or I can use a different notation for this capital T, because I'm using small t, capital T, it might confuse which letter. Let's run out of alphabets. U. U is taken. V. Okay, we'll call it V. Capital V. This function capital V, okay, we want to optimize. Okay, what is V by the way? V is equal to T times x of x divided by p theta of x minus star of t. Correct? This is what I have called as V. Agreed? It's a maximization of an objective function V over T. All of you see that. But observe this, that this V is actually a function of x as well. But I should say that it's a function of both x and t. It's a function of x and t. It's also a function of x. Agreed? Now, what you are actually doing while you are computing this integral is the following. You first solve this optimization problem over t. Okay. So now what you do is inner optimization problem. So now first you do solve this optimization problem. You get a let's say t star, okay, which is the maximum of this function v x comma t, okay, over all t. Okay. Now you plug this t star here and compute this integral and do it for all x. That is what you are doing when you are computing the integral. You first solve the optimization problem with respect to t. You get some value for that optimization problem. Now you take that. So now observe that this t star, okay, is also a function of x. Do you agree? Obviously, right? Because if v is a function of x, then t star is also a function of x. Because we are only solving, we are only taking the maximum with respect to t, and given a particular x, you will have a different maximum. Correct? Let us represent that maximum using some capital T star of x. Correct? Okay. Now, what are we saying here? That there is an optimization problem, there is an optimization that is happening with respect to t. Okay. Now, that objective function for that optimization problem is a function of x. Now, given an x, you will have a particular maximum for this maximization problem. You compute that maximum and then you integrate for all x. That is what your f divergence is. Agreed? Now, what I can do is, suppose I take the maximization out, okay, and write that whatever is there, p theta of x times p theta of x divided by x of x minus s star of t. Suppose, right, I take this, replace this with t star of x. Which is the maximum of.
So that will be px by p theta, right? T star of x into px by p theta.
Is it px? I always make this mistake. Yeah, it's px by p theta. Sorry. X by p theta. Correct. Now, suppose I replace this, this t, right? I solve this optimization problem and replace it with t star of x. Then it's okay, no? Both the integrals are okay. I can take out the max. Do you agree? Because I'm solving the optimization problem anyway, right? At all points in x, I'm solving that optimization problem and replacing that t with t star of x, correct? That's okay, no? Do you agree? What I'm doing it at all x, I'm simply solving that inner optimization problem and putting the solution for it and then computing the integral. Right? Now, this t star of x, basically, let's say that, okay, it's a function that would take a particular value of x and gives you what? A real number, isn't it? A real number which happens to be the solution for the optimization problem, inner optimization problem. Correct? What should be this t star of x be? T star of x is a function that would take x, you give it an x, it will give the solution for the inner optimization problem. Correct? Do you agree? This t star of x has to be this, right? You look at this by definition. It should be a function that would take an x and gives you the solution for the optimization problem. Okay. Now, any questions so far? Okay. Now, instead of t star, okay, okay, before that, let script t, this is a different symbol, okay, script t, denote, okay, a class of functions, okay, from x to r. So basically what I'm saying is, let script t, this is script t, okay, let script t denote a class of functions from x to r, okay, which means that this t star of x is a member of capital T, okay. T star of x is one member of capital T, which means that it is a function that would take x and gives you a real number, which is a solution for the inner optimization problem at all x, okay. But let script t denote all possible functions that would take an x and gives you a real number, okay. Now, if I cannot, okay, let me write that integral down and then I will tell you this. T of x minus this t, what is that? P theta, that is the second term. P theta of x times T of x times P theta of x by x of x minus f of f star of T of x.
Sir,
Okay?
px of x divided by p theta of x.
Every time I make that mistake, huh? Okay. Okay. Now let's say that there is a tx, okay, which is not equal to t star of x. Okay. I replace this with this. So this suppose px is another function, okay, that belongs to script t, and I replace this t star of x by t of x. What do you think, okay, will be the value of this integral compared to this integral? And somebody tell me. You understand? Instead of having t star of x, which gives me the solution for the inner optimization at all points of x, if I replace that with another function t of x, what would that be?
So it will be smaller than the previous one.
It will be smaller. Do you agree? It will be, this will be greater than or equal to, correct? So this is our f divergence. This will always be greater than or equal to f divergence, correct? Because it will be either equal to t of x or less than t of x. They're not equal to t of x.
Sir, other way around, right? We like t star is corresponding to the maximum value.
Max. T star is corresponding to the max. So this is lesser, and all everything here, all of these are density functions that are positive. So t is lesser. T can be lesser at all points, which means that it's the other way around should be, which is that this is greater, correct? It's a lower bound, no? Correct? Is that okay?
Yes, sir.
It's correct now. This integral is over x. Now I can say that df is greater than or equal to the maximum value, okay, that you can get out of all tx that belongs to this class of functions of this particular integral. Minus, now this is px, no, because p theta would cancel out, integral p theta x dx dx over x. Is this do you agree? Why have I written a max here? The reason I've written a max here is that if you take the max of all possible functions in this bucket of functions, okay, your f divergence will be greater than or equal to that. Now, if you can find a function with the bucket of all these functions that is equal to t star of x at all points, then it is exact. The f divergence will be exactly equal to this integral in the right. Okay. Now, if you cannot find a function, okay, that is equal to t star of x at all point, at least find a function, okay, that will give you the maximum value at all possible x amongst t. There can be, let's say that there is one t of x, there is another t2 of x, there is t3 of x, and all that, right? Let's say that none of these are equal to t star of x. Okay. However, I would choose that t, okay, amongst t1, t2, t3, okay, that is maximum of all this, correct? Of course, I need to choose the maximum because here the inner optimization problem, I am actually looking at, if you look at the definition of t star, no, it is actually the maximum of this objective function with respect to t. Now, if I cannot find the maximum at, at all points, or rather, if I cannot find a function that will give you the maximum at all points, I would choose the function amongst all possible functions that are there in this bucket of t. I would choose the one with the maximum value. Do you agree? That's all. We are done. I mean, I will reiterate over this the next class. So what we basically did was we expressed this expectation. Okay, sorry, the f divergence. We carved a lower bound on this by saying that you choose a class of functions, okay, from a bucket of functions. This is equal to, what is this first term? It's pretty obvious now. This is an expectation of t of x with respect to px, okay, minus, this is an expectation of, sorry, I put it different. This should be, nobody corrected me, this is s star of t of x dx. Let me call this x cap, because when you write expectations, no, it's better to write a different dummy variable. This is x coming from px. This is the expectation of x cap coming from p theta. That's all. This is the result. But this is the last function in a GAN. If you can, if people know, if you can relate, no, this is exactly the last function in a GAN. We will see that, you know, in detail next class. That's all. We are done. So now we have expressed. So basically, what we have done, we have expressed the lower bound on F divergence in terms of expectations over unknown distributions. This is the goal, right? We have achieved our goal. So now we know how to compute. Do we know how to compute the first term? We do, law of large numbers, because we have samples from Px. Do we know how to compute the second term? We do, because we have samples from P theta. Now, if you observe, this entire thing now will become a function of theta, right? Because this second expectation is a function of theta. Now, you don't forget what we have been doing. No? We have this network, g theta, whose parameters are theta. We are giving a random z. Okay, this x cap, the output of this is called as p theta, and we have a lot of samples from p theta, and that's what we use to compute the second expectation. We use our data to compute the first expectation, and then we optimize this using gradient descent, which we will see in the next class. But for today's class, what did we do? We wanted to minimize the F divergence. We could not, because we don't know the underlying distributions. The goal was to represent the unknown divergence or uncomputable divergence measure in terms of expectations over underlying distributions, because we know how to compute expectations using law of large numbers. We invoke the property of convexity and conjugates to express the F divergence in terms of expectations over underlying distributions. That's all we did so far. Okay. So before coming to the next class, as I said, no, things are getting more intense and involved. Please go through this content, right? I mean, whatever we did in today's class, go through that once. And if you have questions, you can ask me or TAs either on the WhatsApp group or on Teams. And you also look at the notes that I've given, no, the handwritten notes. This time I've kind of swapped the order. I used to teach VAEs first and GANs then. Now I've swapped the order. We started from the GAN, so it is the lecture 4 in my notes. Lecture 4 in the handwritten notes. I've shared that with you. Please have a look at it and also read the paper. The paper that I am following is that variational divergence minimization. Let me just tell you the name of the paper. It is there in my handwritten notes. This is called F-GAN, okay, which is a generalization of all GANs. It is called F-GAN training generative neural samplers. Title of the paper, okay. Using variational divergence minimization. This is the paper that I am going through, okay, meaning this is what I have, of course, I've created my own narrative, but this is the paper. So it is there in my handwritten notes. Please go through the handwritten notes once and also go through whatever has been covered in this class. and come prepared, please. If you have questions, of course, you can ask me, but do prepare and come back. It will be, yeah, we will continue from here. I'll redo whatever I did this time, okay? So this I will redo, but yeah, have a look at it and come prepared, okay? That's all for today then. Yeah. So for people who are celebrating Happy Ganesh Chaturthi, so we will reconvene next class, next Saturday.
So just one question.
Yeah.
For this theory that you covered, any reference material that we can refer to?
I gave you, no, that's exactly what I told.
I mean, especially on this convex optimizations and such stuff, if you have anything handy.
Convex optimization is a standard stuff. Even Wikipedia says this. I mean, meaning the convex conjugate and the convex functions.
Okay.
Yeah, any convex optimization book would do, but you don't need, I mean, we are not doing convex optimization here, right? Beyond just defining the conjugates, we are not doing anything. So that, I think, standard articles in Wikipedia would suffice. Huh?
Okay. And the paper that you referred, I think that would be also a reference.
And I have given you some references in my handwritten notes. Please have a look at it. For instance, right? I mean, differential conjugates and the related stuff. No, I have put in some of the references at the end of my handwritten notes. Start reading them.
Sure.
Okay. Okay. Anything else?
Just one other question, sir. So this quiz will be on Moodle or?
No. We will do it on this thing, Microsoft Forms.
Okay.
We will not use Moodles. Yeah. We will let you know. Okay. Again, we will intimate that in Teams and WhatsApp.
Sure, sir.
Okay. Thank you. Then we will see. Also, let me know if you think that I mean, class is too intense, or you want some other change, etc. You have that anonymous feedback form that is there on my webpage. You can express your thoughts. When you are writing, please mention that you are from the online version of the course. That's all, so that I know where to implement the change. I mean, of course, it's anonymous. You don't have to put your name or anything, but just mention that this is from the online student, and you can just put in your thoughts if you need any change in the way things are going. Okay. Okay. See you next week. Bye bye.
Thank you, sir. Bye.
Thank you,
Thank
sir.
you.
Thank you, sir. Yeah, thank you, sir.
Thank you, sir.
Thank you, sir.
Thank you, sir.